Welcome back to my video. In this chapter, I'm going to show in this video will show you on Form 4 Physics, Chapter 2, Part 8. Now this chapter, I'm going to I'm going to show you on the understanding of work. What's work done? What does it mean by energy? What's power? And followed by efficiency. There are 4 parts of it. So start with the first part. Work done. Okay. So first part we work done or work. Okay. You have done your work. So what does it mean? Okay. Work is actually a force that causes the object move in direction of force. Okay, it's actually a force that causes object to move in the direction of the force. Okay, the force that causes an object move in direction of force. In terms of equation, you need to look for the value. What's the work value? Work done value. Work is therefore F dot S. Okay. Now, this is a general equation, dot product, where you need to look for the direction of force. That's why you have a direction of force. Okay. Move in direction of force. Before I go down into it, let me define unit for work done. You have a special unit called joule. Okay, or just a symbol J, joule. Okay. So based on this equation, work done. What does it mean by work done? Work done is actually a product. Work done is actually a product of force and S is displacement. Force and displacement in the direction of force, of course, in the direction of force. Okay, that's all about the wording. Now let me give you an example. You will get a better understanding by using the following example. You have an object, okay, over a flat smooth surface. Now you exert a force, center of gravity, force, and a few seconds later, you pull it to the right. Next moment, your object would be displaced here, and it has traveled from here to here of distance S. Okay, so the work you have done to pull this object from left to right over distance S will therefore be summarized. Work done therefore is equals to F dot S. In this case, the direction of force to the right, isn't it? Is parallel to the distance where it has traveled, or displacement it has moved. Isn't it? From left to right. This object moved from left to right. The direction of force is also from left to right. Okay, this is for starter, right? Now, next, same object. Instead of the force is from left to right, now a force exerted by an angle of theta, of any angle. Okay, just enough to displace an object from left to right over the same displacement, you may say. Okay, so this object move from here to here. What is an S? Now please take note, the direction of force is now an angle. Okay, so you can't, the work done is therefore you thought is Fs. Yeah, it's not. It is not the case, because now the direction of force is at an angle. So you need to look for the direction of force parallel to the displacement. This is left to right. So all you need to do is, yes, if your instinct right, you need to get this force. I mean, what is this horizontal force? Because the object is travel from left to right. Okay, you may do it this way. So therefore, this horizontal force is actually F cos theta, right? Because cos theta is actually horizontal over F, right? So therefore, the horizontal is therefore is H cos theta. Okay, cos rule. So therefore, for this case, when the force is no longer parallel to the displacement, or the displacement is no longer parallel, or normally you use a force, okay? If the force is no longer parallel to the displacement, where the object moves from one side to another, then you need to look for the horizontal force parallel to the displacement or the movement of the object. Therefore, this equation would be W, work done will be equals to F cos theta times S, displacement in meter. Okay, so this is what it meant by that. Or we rearrange it, is actually Fs cos theta in terms of magnitude, right? So you get the unit as in joule. So this is all about it. You need to find out this is the hard part, okay? F, the horizontal, parallel to it. And it's important only for initial and final. So this is initial, and this is where the final position. Okay, what happened in between is not so much of an importance. Now let me give you an example towards it. What does it mean by that? Next page. Now what happened now is, what I've given you in the previous page is what? Left to right, simple, right? Now, if you were asked horizontal surface, and there's a book lying on it, horizontally, okay, on the table, resting on the table. Okay, maybe this on the table, 3D. Okay. Oh, I think it's not related, but I just want to let you know this table, this book is lying on to the table. Okay, on the table. Okay, now, if in the event you ask, if I were to flip this table, I mean by fixing here, I fix it here. If this book flip 90°, and it turns out to be, you flip it 90°, next moment it turns out to be like this position. Would there be any work done? Because based on our definition that define W is what? F dot S, right? You say, oh, the direction of force must be parallel to the displacement, right? And then when the force is with an angle, then you look for the horizontal force, right? Horizontal component of the force, which is parallel to the displacement or the movement. So how about this? I mean, they don't seem to have any movement, isn't it? Right? No, it is not. Let me enlighten you on it. What happened is, we always draw the center of gravity. Based on this here, the center of gravity shifted, right? From here to here. I mean, I think easier would be look at it sideways. If I look at it front view, what happened is, here, the book turns out to be from horizontal position, and then flip to here. When it flipped to here, what happened? The center of gravity is actually being raised from my base. This is my reference, this is my 0. Okay, so there's an increase. Okay, so here to here, there's an increase. This will be my S, displacement. So there's an increase of center of gravity, like what happened you draw a free body diagram from previous video. Okay, so therefore, yes, there's a work done. So yes. How? Therefore, my work done would be, force is actually mg for this case, because the mass of the book and also the gravitational mg. It doesn't need to cos theta because the weight of the book is downwards, right? This is g. You are doing work to go against the gravity. Okay, against the gravity. So therefore, this is my F. Then therefore, this is my displacement, which is h, or this is actually h, or defined as S. This is where an increase of potential energy, because this is where I define my potential is equal to 0. I define the table as 0. The potential increase by a distance h. Okay, so there's an increase of potential, special unit case. Then the rest will be quite easy already, because you have got the idea. Now what happened is, you were to go up a stairs, and then maybe you go down in the playground, perhaps, maybe. Okay, a slope. Okay, slide through. Okay, right. Okay, now what happened is, a person climbs up the hill, climbs the stairs, and then go down, slide down. But we are not going through this guide down yet. It's not there yet. Okay, let us focus at the first part here, where the height of this person, height for this stairs would be, says, maybe 60 centimeter. Okay, maybe I will define this height would be 60 of a centimeter. Okay, so of course they will let you know, oh, one stairs is how many centimeter, how many stairs, and eventually you know the total height. Okay, and this person's weight maybe 60. No, it's a kid's, maybe a 2 kg load, or 2 kg, or perhaps 2 kg is maybe it's too small. Maybe it's 20 kg. 20 kg. Go up the stairs. Okay. Then it asks, what is the work done by this person to go against the gravity? So what the work done? Work done against gravity. Gravitational pull, gravitational force. Gravitational force. Okay. So normally the question wouldn't say that. Yeah. So normally they would just ask for work done, but since this is a tutorial, so this is actually work done to go against the gravitational force. Okay, what's the work done to go against gravitational force? Gravity is downwards, but you are going upwards. Okay, this is where the gravity down. Okay, you're going upwards. So therefore, according to the law, it doesn't really matter what's the process, whether it's a stairs or a slope or whatever it is. What's important is the initial, and where it stops here. This is the final spot. Initial and final, what do they have different in terms of height? This is where the direction of force up and down, and there's an increase of 60 centimeters. So therefore, the work done easily would be equal to my mgh, which is your m is 20, g is 10, h is centimeter. You need to convert it into SI unit, which is 0.6 joule. Okay, 120 joule. Okay, that's it. Okay, so this is where the gravitational force, where downwards, and the force is upwards. So it doesn't really matter upward downwards, but the gravitational force is up and down, and there's an increase of height. So it doesn't need to make use of the cos. Okay, there's no need. Okay, because the gravitational force is downwards. This is a total distance increase. So there's an increase in potential difference, and it's actually work done to go against the gravitational force. Right? Okay. So next, that will be called energy. Second part is called energy. Now energy is related. What does it mean by energy? Energy, what do you know, is actually a capacity. Ability, right? It's a capacity or an ability. It's an ability or capacity to do work. Ability, to me I think it sounds more logic. That would be keupayaan. Okay, it's an ability to do work. If it doesn't have energy, then you can't do work. Okay, SI unit for energy is also joule, similar to with work. Okay, and good news is energy is just a magnitude. Okay, it's just a value. It's a scalar quantity. Okay, and unlike work is actually you have force. Force is therefore it's a vector. Okay, now in energy, something you will learn would be called principle of conservation of energy. So this is a principle that you need to learn, and maybe this is the first time or maybe this is the second time you learn the principle of conservation of momentum. Now here is principle of conservation of energy. Okay, conservation of energy, what it says that this is where the energy, it says energy can be created, or nor destroy. Okay, you can't destroy an energy. Okay, but it could be transferred or transformed. Could be transformed into other energy. Be sure important. The total energy, no matter how you change it, the total energy of the system is conserved, or you call it as a constant. What does it mean by that? Now it means, for this case, initially and finally, initial spot, final spot, I gain potential, meaning an mgh is potential energy. Potential energy. What happened when it's a potential energy so high up, when it comes down, glide down to here, doesn't really matter. This is a curve. Once it came down, what happened during the process of coming down? All the potential energy would be transferred into movement, right? This is called kinetic energy. Okay, where potential energy is mgh, all the energy will be transferred into kinetic energy is half mv squared. V is the speed. Okay, so this is how would it be? Or maybe you will have friction, then you need to plus frictional force, frictional energy, energy to overcome frictional force. That it will be here and equals to mgh. You can't destroy it, okay? Well, this is basically all over it. It will normally from potential to kinetic, and what is the interesting part is this velocity, because when the good question doesn't give you velocity, you need to relate to the previous chapter, not previous chapter, previous video in the same chapter, where we have v squared equals to u squared plus 2as. You need to make use of that 5 equation. Okay, most of the time you need to use this equation. Okay, but maybe it's not restricted to, but most of the time use this. Okay, it doesn't give you the speed, and you need to look for the speed. Okay, you may pause this video because I'm going to continue. Yeah, you may pause this video, look for the equivalent questions. Yeah, from work and energy, chapter by chapter workbook. You need to have at least maybe 10 questions each. You have about 20 questions. You need to try 20 questions on this before proceed to the next section called power. Third part, power. Okay, now in terms of power, it's pretty easy. What does it mean by that? It is governed by this equation. P is equals to E over T. Okay, E over T. So what is power? Power is actually a rate of change, because whenever you have an over T, it's a rate of change. Work is done. Rate of change, work done. Change for work. Rate change, work done. Or rate of energy transform. To be put away. Rate of energy being transformed. Okay, how fast energy changes from one to another. Okay, or rate at which work is done. Okay, or rate of which work is done. Okay, it's always work per unit time or energy per unit time. Okay, maybe put it the other way, or it's also equals to work per unit time. Okay, the they are of equivalent. That's why you put it. That's why I put it into equal sign. In terms of unit for power is actually watt. W-A-T-T, capital W, and it's just a value, right? There's no direction. In this case, for power, it's actually a scalar quantity. There's no, okay, there's no direction to tell. Okay, you just need to take the magnitude of it. Okay. Now, if you look carefully with this equation, especially for work rate at rate yeah, rate of which work is done. When you inspect carefully, what happened is P is W over T. Now, W work done is F dot S over T, right? How you get work is force dot displacement. What happened when you have rate change of displacement? Your equation will turn out to be P is V. This is velocity, rate change of displacement. Okay, so there are, you may say, two equations, power, first one, and the second one. But I will say there's only one, okay, because this is a derived equation. Work rate change at which work is done, W over T. But it's also equals to force times velocity, because it's derived here. So if you want to find out the power of a car, you take out the force, thrust, and the velocity, then you will be able to find out what is, or the other way around. They let you know how much horsepower, convert it to watt, and then you divide its velocity in SI unit, then you know what's the force, pushing force. Okay. You may want to pause this video again because it's quite short. It doesn't need to go through extensively about power. Stop this video, pause this video, look for similar question about power. Maybe 5 questions will do. It's pretty straightforward. Okay, 5 questions. Then only then you proceed to my fourth part, which is the last part. Last part here is called efficiency. Okay, efficiency. Do they have a symbol? Yeah, I think they have. It's called eta. Pronounced as I-T-A, eta. Okay, but doesn't really matter, even if it doesn't know. I mean, maybe sometimes later you come across with some physics book. You may go through it. So, what's efficiency? Yeah, efficiency actually compares the useful output energy to the input energy. So if you want to put into an equation, therefore the efficiency is actually the energy of the output over energy of the input, and then you times it with 100%. Okay, where will you normally see it? You will normally see it in it's actually loss of energy. It's caused by, why do you want to know about efficiency? Because there's a loss of energy during the transformation. Okay. Another simple graphic design, and it graphically represents. Says you have a motor. Okay. Input power, electric power. Then you get the rotational speed, right? Rotational speed, which transform to output power, isn't it? Then you compare the output to the input times 100%. Then you know how's the efficiency of your system. Okay. That's actually basically about it. You may go through your reference and text. Okay. Read through the experiment and find out the efficiency. Why is it important? Importance of efficiency? Because it's all about energy loss. You want high efficiency so that you have low loss. That's the main purpose, right? If your efficiency is high, therefore your loss is low, then you need to pay less, meaning you need to pay less. High efficiency, low loss of energy. Okay, that's not much of exercise for efficiency. Normally, if you know how to find out the output energy or output power, then you should be able to get the efficiency. Okay, sometimes in power, sometimes in energy. Okay, so or it could be an energy. Could also be P output over P input times 100%. They are similar. Okay, all right. So that's all for this section of video. You need exercise, practice and exercise, and as well as with your reference text. Look for the experiment. What are the experiments conduct to test the transfer of energy, especially from kinetic to potential kinetic? How to make use of that and find one of the parameter. I'm sure you can do it yourself at home. I will not be there to help you out with it. You may ask your friends or teachers around it. Group discussion. Yeah, at least you must have your own practice exercise. You cannot just watch all this video and you thought you know of it. There's no way to do it, and that's not the way how physics you were able to practice physics questions during your SPM. You can't score an A by just watching all my video. You need to practice yourself at home. I hope it helps out with you, especially in your studies. Maybe you watch this video, then you go for your class. That's all from me this time. Stay tuned to my next video.